Okay, so we've got two more things to look at in relation to the calculations involved in volumetric analysis. One of them, as you can see from the title here, is looking at the reactions between a solution and a solid. And the second one, which I'll do towards the end of this session today, involves looking at reactions between a solution and a solution. Now, if you think about it, you've got a solid versus a solution, and you have a solution versus a solution. Okay, now the lovely thing about this is no matter which one of these two they're going to ask you, something will always be given about one of them to allow you to calculate the number of moles of each. That's always going to be your starting point. Okay, so if they give you a solid, they might say 10.9 grams of this solid. You turn that into moles. Or instead, they might say a certain volume of a certain concentration. And you already know from your triangle that moles is equal to concentration times volume. So therefore you can work out the moles. But the key thing to remember in all the questions I'm about to do is that one of the species mentioned will have enough information to get it into moles. And once you get it into moles, then that will allow you, by stoichiometry, to get the moles of the other reactant, whether it be a solid or whether it be a solution. And the best way I think to do this section will be simply to take it in steps of examples, to do a number of examples of each case. All right, so we're going to just go through the notes on this first. Excuse me, a frog in my throat. Now, in a number of chemical reactions, solids will react with solutions. So that could be iron reacting with acid. It could be something like sodium carbonate reacting with an acid. It could be something like citric acid crystals reacting with sodium hydroxide base. But the key thing is, in some reactions, you've got a solid and you've got a solution. One of the things I want you to remember is this. One of them will be convertible to moles. Okay, keep that in mind. One of them will be convertible to moles. So, your solute and your solvent, just in case you're wondering, you'll either be given the volume of solvent and its molarity, so therefore you can multiply those two together to get the number of moles, or you'll be given a number of grams of solute, one or the other. And from whatever is given, you turn it into moles. Okay? So we apply the principles of stoichiometry in order to calculate the amount of solid that is needed to react with a given volume of solution. And of course, it's the other way around. We could also apply the principles of stoichiometry to calculate the volume of a solution that's needed to react with a certain amount of solid. But one of them will be given in terms of a quantity. Substances then, once we figure out where to begin, they will be compared through moles. Now, how do we compare them through moles? By using a balanced equation. And in every one of the examples I'm about to do, there will be a balanced equation at the heart of the question, which will reveal something interesting about how we compare the number of moles of one substance to the other. I suppose I would say, and I would preempt this section by saying, if you haven't studied your stoichiometry very well up to now, pause this video now and go back on your stoichiometry, take a good long look at it, study it well, and when you understand what the principles of stoichiometry are in terms of the balanced equation, then come back and give this a go, okay? But you do need to have the stoichiometry well understood before you can move on. Remember that in the balanced equation, the ratio of reaction is all important. Now, what do I mean by the ratio of reaction? The coefficient of the reactants. 1:1, 1:2, 2:3, whatever it's going to be. They are vital. They're part of your calculations. So I'm going to go straight into an example. What mass of magnesium will react with 50 centimeters cubed of a 0.5 molar H2SO4 solution if the balanced equation for the reaction is Mg plus H2SO4 reacts to give magnesium sulfate and hydrogen gas. Now, here's the first thing I want you to notice. Take the balanced equation. Always go to your balanced equation first. Look at the two reactants. Look at their coefficients. Both of their coefficients are an invisible 1. So therefore, the ratio of reaction is 1:1. What does that mean? That means that the number of moles of both will be exactly the same. So all I've got to do now, step number 1, is to work out the moles of one of them. So go back to the question and see what information is given. Nothing is given about magnesium. We're simply asked about what mass of magnesium. But we are told the volume, and we're also told the concentration of the acid. And you should know from your triangle that moles equals volume times concentration. That's the formula triangle. So in other words, if I multiply those two together, I'll get the number of moles of sulfuric acid. Okay, so let's do that. The volume, please, in litres, so divide it by 1,000 if it's in centimetres cubed. It's going to be 0.05 litres. That's your volume. Multiplied by our concentration, which is 0.5, will give me the number of moles. Now, I'm not taking any chances. 0.05 by 0.5 comes out as 0.025. So now I know that I have 0.025 moles of H2SO4. So, how many moles of magnesium will I have? Well, look at the balanced equation, look at the reaction, look at the ratio. The ratio is 1:1. So if I have 0.025 moles of sulfuric acid, because the ratio of reactions to 1 is 1:1, I'll have 0.025 moles of magnesium. Now, once I know the number of moles of magnesium, I go back and figure out what are they asking me to do. They're asking me to go from moles to mass. And the quickest way to do that, working away from the mole, is by multiplication. And the key link number between moles and mass is the mass of the substance as given on the periodic table. So you go to the periodic table, you find magnesium, and on your periodic table, magnesium comes out as 24.31. So therefore, 24.31 grams will be 1 mole. And you simply multiply 0.025 by 24.31, and you end up getting 0.6077. So you could say, if you want to round it off, 0.61 grams of Mg. So very similar to the stoichiometry questions that we had before. But again, please keep in mind, one of the species will always have enough information to turn it into moles. And then you simply distribute the moles through the reactants according to the ratio in the balanced equation. Okay, let's take another one. Sodium carbonate reacts with dilute hydrochloric acid according to the following equation. Na2CO3 plus 2HCl will react to give sodium chloride and carbon dioxide and water. Now, the very first thing I would do when I'm given a balanced equation is write down the ratio of reaction. And the ratio of reaction here is 1:2. Okay, so that means we've got to take that into consideration now when we're going back to compare the number of moles. Let's read on. What volume of hydrochloric acid of concentration 0.75 molar would be needed to neutralize 7.5 grams of anhydrous sodium carbonate? Now you've got to ask yourself a question. Which one of the two species can be turned into moles? Well, we can't turn the hydrochloric acid into moles because it only gave me molarity. And we need molarity times we need volume to give me moles. So I don't have the volume. So I can't start with the hydrochloric acid. But I can start with the sodium carbonate. Anhydrous just means without water. 7.5 grams. How do I turn grams to moles? And the answer, I hope you remember, is by division. You take the 7.5 grams of anhydrous sodium carbonate and you divide it by its own molecular mass from the mass as given on the periodic table. Now, sodium is 23, so Na2, that's 23 twice, which is 46. Carbon is 12, and 3 oxygens is 48. That's 106. So this is going to tell me the number of moles of sodium carbonate. And 7.5 divided by 106 comes out as 0.071. 0.071 moles. Okay, so that is your Na2CO3, sodium carbonate. Now, go back to your reaction, your equation. The ratio of reaction is 1:2. So therefore, there will be twice as much the number of moles of HCl as there is Na2CO3. So when I multiply 0.071 by 2, and again, don't take chances, always use your calculator, you get, as we expected, 0.142. 142 moles. Okay, of HCl. Now, is that what the question asked me? No, the question asked me what volume. So now, because concentration is needed, I need to go back to my triangle. What's my triangle? Moles, volume times concentration. So from this, if I want to work out what volume, that gives me the formula. Volume equals moles over liters. Okay, or sorry, over concentration, I should say. See, moles over concentration. Well, there's the number of moles. Where's the concentration? There it is, 0.75 molar. Yeah, the capital M is always concentration. So if I want to work out the moles of HCl, or the volume, I should say, of HCl, what am I talking about? Gone mad. If I want to work out the volume of HCl, go back to your formula. The volume is equal to moles over concentration. So it's moles over concentration, which is 0.142 moles over a concentration of 0.75, and 0.142 divided by 0.75 comes out at a volume of 0.1893 litres. Now, if they ask you for centimetres cubed, just keep in mind that there is 1,000 centimetres cubed in a litre. So that's also equal to 189.3 centimetres cubed. Okay. So again, you'll notice in that there was enough information given about the sodium carbonate to turn 7.5 grams into moles. And we did that by division of the mass of sodium carbonate, which is 106. We got 0.071 moles of sodium carbonate. We then go back to the balanced equation and recognize the fact that twice as much moles of HCl are required. So I multiply that by 2 to work out the number of moles of HCl. And then, because the question asked me for volume, I've got to go to the formula triangle. Moles over concentration is equal to volume. So you write that down. Volume equals moles over concentration. You take the moles, which is 0.142, you divide it by the concentration, 0.75, and you get an answer of 189.3 centimetres cubed. Now, as I said, there are two examples. The first example is a 1-to-1 relationship. The second example is 1-to-2. I'm going to give you two questions to do. This one here, which you can now pause and work on, and this one here, which you can now pause and work on. Okay, I'm going to come back to these two questions in our live class. I want you to try these as best you can and see if you can work out what the questions tell you. So that's the first part. The second part is where we have a solution versus a solution. Now, in chemistry, when we're trying to use one solution to work out the concentration of a second one, there's a number of things we've already learned. Number one of the solutions has to have a concentration that's known. That's a standard solution. The second one doesn't have to have a concentration that's known, because we will discover that using the titration formula, which I'll develop now in a few moments. But when you're basically reacting to solutions, you do so through the method called titration, okay? Because the titration allows me to pinpoint the end point of that reaction. And because we're dealing with acids and bases in this chapter, the end point of an acid-base reaction is obviously neutralization. So put it all together. If you're titrating an acid and a base, you're using that method to pinpoint the point of neutralization. Now, first of all, what is neutralization? Neutralization occurs when the number of moles of the acid is exactly the same as the number of moles of base. Because at that stage, they will cancel each other out and they'll form a salt and water. Okay, so keep that in mind. Titration allows me to pinpoint the point of neutralization between an acid and a base when the number of moles of acid is equal to the number of moles of base, which we will discover now by calculation is an easy thing to find. Okay, so let's move on to what we talked about there a few moments ago. When carrying out a titration, and there's your titration method. Some of you may have done this for junior cert, some may not have done this for junior cert. We've got plenty of them to do, so there'll be plenty of practice with the hands-on experience once we get back to school. So when carrying out a titration, we are looking to find out where the end point of a reaction occurs. And as I said already, in an acid-base reaction, the end point is neutralization. Therefore, the formula V1M1 equals V2M2 can be used. Now, only if the ratio of reaction between the acid and base is 1:1. Some people prefer to call this VA MA equals VB MB. Now I think you can make sense of what that means. The volume of the acid multiplied by excuse me, multiplied by the molarity of the acid is equal to the volume of the base multiplied by the molarity of the base. Why? Because Vm gives me the number of moles. Okay, the volume by the molarity gives me the number of moles. And likewise over here, Vm for the base gives me the number of moles of base, and only when they are equal have we reached a point of neutralization. So keep that in mind. Now again, best way to do this is by means of a number of questions. So let's take this question here. I'm going to do 2 questions, and then I'm going to leave you with a further 3 to do yourselves. Okay, and again we'll come back and look at these in the live class. It takes 83 centimeters cubed of a 0.45 molar NaOH solution to neutralize 235 centimeters cubed of a HCl solution. The balanced equation for the reaction is as given. Sodium hydroxide plus hydrochloric acid reacts to give sodium chloride and H2O. What is the concentration of the HCl solution? Now, in this question, notice we're dealing with an NaOH solution and a HCl solution. So we're dealing with the reaction between 2 solutions. So therefore, solution 1 should have a volume and a molarity, which it does. There's your volume, there's your molarity, V and M. And solution 2 should have a volume and a molarity. Well, there's your volume of the second one. And they're asking me to work out what the molarity or the concentration of the second solution is. So therefore, you've got your V1, M1, and you've got your V2 and M2. And the only one of these that is not known is the concentration of the HCl, which I'm going to call X. Volumes, please, in litres. So take your 83 and divide it by 1,000 to get 0.083 litres. And likewise here, 235 centimeters cubed is 0.235 litres. Okay, so now that I've done what I call the preparatory work, let's go to the balanced equation. That's the most important thing. In the balanced equation, what is the ratio of reaction? The ratio of reaction is 1:1, which means that if I can work out the moles of one of these species, I automatically have the number of moles of the second one because they're equal. The ratio is 1:1. So what formula do I use when I'm using 2 solutions? Answer: V1 M1 equals V2 M2. So let's go back over the question. The first volume mentioned, V1, is 0.083, and that's multiplied by its corresponding concentration of 0.45, and that in turn should be equal in the second solution to its volume, 0.235, multiplied by its concentration or its molarity, which in this case is X. So in order to get X on its own, I'm simply going to divide both sides by 0.235. So 0.083 multiplied by 0.45 over 0.235 is the value of X I'm looking for, which will be the concentration of HCl. So let's work that out. Go to your calculator. Apologies for my voice. I have been talking all day long. It's easier for me to do, but I pay the price afterwards. Okay, fraction on. 0.083. It's handy to turn them on first before you actually use them. Turn on your fraction. 0.083 multiplied by 0.45 to be divided by 0.235, and that comes out as an answer of, let me try that again, 0.083 multiplied by 0.45 over 0.235, that's better, equals, and the answer there comes out as 0.1589. So 0.159. And because it's concentration, just put a big M after it. Now I don't mind. You can put down 0.159 M, or you can put down 0.159 moles per litre. Both of those are exactly the same. Capital M means moles per litre. So just realize that those two symbols are exactly the same thing. Okay, so that's the first one. And that is easy enough to work out if the ratio is 1:1. But what happens if the ratio isn't 1:1? What happens if you end up with two solutions reacting together in a ratio that might be 2:1 or 3:1 or 2:3? How do we change the V1M1 equals V2M2 to reflect the fact that the ratio of reaction is not 1:1? And the answer is easy. You take the V1M1 equals V2M2 and you divide the respective sides by the coefficient of the reactants. Now, it's all very nice to me to say that to you, but in practice, what does that mean? It means that you still have your V1M1, that's still going to be the number of moles of your acid, that's going to be the number of moles of your base. But if your acid and base are not in a ratio of 1:1, the corresponding ratio has to go beneath each species, okay? So if, for example, it was HCl, NaOH 1:1, if it was NaOH and H2SO4, that's 2:1. So that means that these numbers here would be brought into play as 2:1. And again, I'll give you an example about that in a moment. Take this one here. It takes 38 centimeters cubed of 0.75 molar NaOH to completely neutralize 155 centimeters cubed of a sulfuric acid solution. The balanced equation for the reaction is as follows. 2 NaOH plus H2SO4 react to give Na2SO4, that's sodium sulfate, and 2 H2O. Now, what's the first thing I notice? The first thing I notice between the reactants is the ratio of reaction is 2:1. Okay, so I'm still going to be using V1M1 equals V2M2. However, because of the fact that it's 2:1 of NaOH and H2SO4, I've got to put that ratio under each one. So this side here is going to represent the NaOH, and this side here is going to represent the H2SO4. And all I've got to do then is fill in the numbers. So let's read it again. It takes 38 centimeters cubed, there's V1, of 0.75 molar, that's M1, to completely neutralize 155 centimeters cubed, that's V2. The balanced equation is blah blah. What is the concentration? So in this case, M2 is going to be your X factor. We don't know what the concentration is, so we simply call it X. So what does that come out as? Well, let's take the NaOH first of all. 38 centimeters cubed is 0.038 liters, okay? And 155 centimeters cubed is 0.155 liters. And we prefer to use liters. It just makes life very simple for chemistry. Equals, so let's do the first one. V1M1, so the first volume is 0.038. And that's multiplied by its concentration, 0.75. And because that represents NaOH, I go down to the balanced equation, and the number in front of NaOH is 2, so that's divided by 2. Then go to the acid. We've got 155, that's V2, 155 so 0.155 litres, multiplied by its concentration, which we don't know. So we're going to call that X, all over 1, because in balanced equation, the number in front of H2SO4 is 1. Now, you've got to pull out all your algebra here. In order for me to get rid of 0.155 as a multiplier of X, I'm going to divide both sides by 0.155. So instead, I'm going to take that from there, and I'm going to put it down here. Because it always divides on the other side. It always does the opposite on the other side of an equation. So therefore, what's X equal to? Well, X is equal to whatever your calculator tells you that mess over there on the left-hand side is. So turn on your fraction. 0.038 multiplied by 0.038 multiplied by 0.75 over 2 times 0.155. Now be very careful when you're using a calculator that you press your brackets fully, otherwise it'll give you an error. So 0.038 by 0.75 over 2 times 0.155. Answer comes out as 0.0919. Now, I would simply say that's quite easy to write down as 0.092. And what are they asking me about? Concentration. So big capital M after that. Or if you want to, 0.092 moles per litre. Totally up to yourself. And that's the concentration of H2SO4. That's it. So again, we were given information. We did start with the information that would allow us to get the number of moles. There it was. We were allowed to work out the number of moles there. of the NaOH because we were given a volume and given a molarity. With the H2SO4, we were only given a volume. So therefore, we turn the 38 centimeters cubed of 0.75 molar NaOH into moles, and we divide it by 2 because of the 2 in front of the NaOH. And then we take the 155 times X and divide it by 1 because the coefficient of H2SO4 is 1, and then we do simple algebra in order to isolate X to get the answer. Now, I'm going to leave you with these three. This one, so you can pause and do this one. Then this one, so you can pause now and do that question. And this one here, pause and do that question. These are the heart of what we're going to move on to with titrations. Every single titration reaction involves using the formula V1M1 equals V2M2, and both of them divided by their ratio of reaction, their coefficients. Okay, but we'll come back to that when we're dealing with titrations later on. For the moment, I want you to tackle those questions. I'm going to go through them with you in a live class. In the meantime, if you have difficulties with them, send me an email and we'll get back to you.